Hi, I'm Dr. Miller, mathematician. I'm here to tell you that I was wrong about something. That was in one of my last videos that I created. I was talking about zero, and I was proving various um, rules based upon the definition of, of how we make numbers. But one of the things which I ran into is that I made assumptions on certain rules, which I didn't really share with you. And when I thought about it, I realized I was going on the assumption that zero was nothing, which is exactly what I was trying not to tell you. And what I found that during that time, as I was looking at other YouTubes by other prominent mathematicians, and found that their proofs also left things to one's imagination. And so, what I'd like to do is go through and really show you the process and where the proof was and how I discovered that I made a mistake. Okay, so let us begin, and I will now do a share of my presentation with you. And it's only a few slides this time. So part of it will be review. And the review was, as I said, I wanted to make sure that I could prove things without the assumption that zero was nothing, that would be a conclusion in terms of how I might interpret certain problems. That wasn't how I was going to prove things. Now, what I basically said is the way we create numbers is adding one to the previous number. And so one would be created by adding one to the previous number, which on the number line would be zero, and on the clock would be 12. And three would be created by adding one to two, which was the previous number. But I could take this one and replace it by z plus one. So I would now get two plus z plus one. But now I'm going to use the commutative process to interchange these two and then use the associative process to add them. So this gives me that 3 is equal to 3 plus z. And simply by induction, I can prove that for the rest of the integers. But I haven't proved to my satisfaction that z plus z is equal to z, and that when I add z to fractions, that it's not necessarily the case, which I'm not going to handle at this particular point in time, but you'll see the logic and why one has to do that. Well, maybe I will, we'll see. Okay, and so also what happens when we multiply by z. Okay, so first thing we do is we try to prove some of the things we have already. So what I did was subtract z from using subtraction, and we find that not only is 3 plus z equal to 3, but 3 take away z. So simple little step, but I didn't prove that. Okay, and then we also, which we'll use later on, is that when we take 3 away from itself, we get z. And all of that is because subtraction is reverse addition. Okay, then when I went with my negative numbers, I basically can show here that since minus 1 is before z, if I add 1 to minus 1, I'll get z. And if I use, again, my subtraction, I get minus 1 is equal to z minus 1. And notation-wise, we just drop the z. Okay, so now I proved that we can add and subtract z from, itself in negative numbers. I could in another step there. But then I was interested in another thing, and that was, oh, yeah, z added to a negative number. So I know the 1 minus 1 plus 1 is equal to z. And what I'm in this case doing is subtracting 1 from both sides. And from here, I can see that z minus 1 is minus 1. And here I got 1 take away 1, it's also z. So when I add z to negative 1, I get negative 1. So what I've done is I've gone through and said, I'm not going to just take it for granted, though you may look at it and say, well, I knew that already. But I'll show you later on why this bothered me. And this is what makes many of us feel uncomfortable with mathematics. We feel that something is being left out. So now let's go to our next slide. And what we have now here is let's see what happens when you multiply by 0. So again, we start off when we add 0 to 1, we get 1. But now I'm going to subtract 1 from both sides. And 1 minus 1 we know is z. And 1 minus 1. And so when we add z to z, it gets z. Oh, I feel so much better. Now I've seen that z, when z is added to itself. When it's added to negative numbers, when it adds to positive numbers, I get the same thing. Okay, but now we take a look at this and we say, well, what would be 5 times z? Well, for our definition of multiplication, it would be 5 z's. Don't go to sleep on me, please. Okay, and I know 2 of these can be replaced by a z. 2 of those can be replaced by a z. So I'm left with these 2 z's that I just replaced plus the other z. And those 2 I can replace by z. So little by little, I reduce it down to have z plus z, which I know is equal to z. Now, here's where a problem comes in. We just sort of accept things. We just accepted multiplication as repeated addition. But I'm going to slightly redefine multiplication where it'll still give me the same results. And that is, instead of just being repeated addition, it's adding the number to 0 or z several times over. And what happens in this definition, what I see is that 3 times 5 is 0 with 3 5s, 2 times 5 is 0 with 2 5s, and 1 times 5 is 0 with 1 5. And so 0 times 5 would just be 0. And this is sort of interesting because now I see over here I proved 5 times z was 0 was equal to 0. Now I'm proving that 0 times 5. Well, that's the commutative property. I wasn't willing to accept the commutative property, but this now makes me feel more comfortable. You might not necessarily feel it's a proof, but it's a confirmation. And that's what's really happening in math. That's why people can teach math so many different ways, some of which I think are good and some of which I think are terrible. And the reason for it is because it's the way we interpret and look at things. So now we see that we're more comfortable that we've also illustrated with this that 0 obeys the commutative property. Now we're going to do multiplication by negative numbers. Okay, and so 5 times negative 3, well, I would do a count. 5 of those negative 3s, and I know that 0 added to negative 3 is still 3. But what are 5 negative 3s are? Well, if I look over here, I know that a negative number added to its inverse, a negative added is 0, and 0 plus 0 is 0. If I group them, well, before I group them, I actually interchange them, which is the commutative property, and now I group them, and so I get minus 3 plus minus 5 plus 3 plus 5 is equal to 0. Okay, so I now move this over to the other side, which is subtraction. I get minus 3 plus minus 5 is equal to 0 minus 3 plus 5. And we've already shown that we've defined negative numbers. A negative number is equal to the positive number subtracted from 0. So I can make this minus 3 times 5. So I proved this. Some other proofs, they may give you application proofs, or they may create some other things. In one case, I saw where they made vectors to try to explain why this happens. Maybe they wanted to give you an introduction to quaternions. But, and this is the problem with math, we just throw things in there in which we've applied them. And if one works hard enough, they could probably find applications to prove otherwise. So, you ask me what the square root of 1 is, it could be plus or minus 1, not just one answer. Ask me what the cube root of 1, and I get into complex numbers and 3 answers. All of a sudden, this makes me start questioning some of my rules. Okay, and so we restrict how the rules are used. Now, we already know that z is equal to z times 0, 0 is equal to 0. So I'm going to put these 2 zeros in as my definition of negative numbers. And then I use the distributive property. I just love the distributive property. That's the one that I really fully understand, but I feel better and better as I use it over again. So I multiply the 3 times the 5 times the minus 3, the minus 5 times the 3, and the minus 5 times the minus 3. And I already know that 5 times minus 3 is equal to minus 5 times 3. Or we can do it over here, minus 5 times 3. So that would disappear and leave this term left. And so what we end up having is that these two of the, one of the minuses cleared it out. Okay, and now when we move this over to the other side, we get 0 minus 5 times 3. And we know when we subtract a negative number, we get a positive number. We illustrated that in one of our earlier presentations. Okay, and so now we have now see that 5 times 3 is equal to minus 5 times minus 3. But now we'll do something interesting. And this is where I was wrong. Before, what I did is I assumed that a negative number times 0 is 0. With all the fuss I was making, I can't use that as an assumption. That's assuming that 0 is nothing in that basis. But what I find now is if I multiply minus 3 times 0, I can replace the 0 by 5 plus minus 5. So I get 3 times 5 and minus 3 times minus 5, which I know is a plus 5. And these two add together and they give me 0 directly. Now, one of the proofs I saw, they did something very similar to this. Okay, so what we've done is we've now proved everything with the numbers. I have to be careful with everything, but we proved a lot with the numbers, that we can add and subtract 0 to numbers, we can multiply 0 to numbers, and we can predict what the results would be. And you may look and say, you know, it was so much easier when I could explain everything by saying that 0 times 0 is equal to 0, or 0 times any number is equal to 0, because 0 is nothing. And I tried to illustrate to you, there were some examples that came up that wouldn't help with that explanation. For example, 0 factorial is 1 and 2 to the 0th power is 1. Okay, and so it's these kind of contra examples that make me be a little bit more careful on the calculation. And why do people insist upon doing this? I think they insist upon doing this because they don't have confidence in us as students. They think that we have to be spoon-fed this stuff. And my expectation is that's not really the case. The stuff that I'm showing you, I've taught second graders. You say, well, maybe they're smart second graders. Well, maybe there are lots of kids that are smart. But let's now get on to why I came up with this challenge. Okay, and so what we have is, what we know is about 0 added to itself is 0, 0 times 0 is 0. 0 added to its inverse gives me 0, and once negative number subtracted from another number is added, and the negative number times the negative number is a positive number. So remember, we're talking about 12. Well, on the clock, if we go 12 hours, we're back to 12 again. So 12 plus 12 is 12. And if we do that several times, we'll be back to 12. So if we did it 12 times, we would be back to 12 different times. So 12 times 12 is equal to itself. Not 12 times 12 is equal to 0, because multiplying by 12 gives us, because 12 is nothing. That's the way it turned out in terms of the way I designed things. And now 11 is the number before 12, so it could act like a negative number or a negative 1. We add 1 to 11, we get 12. We add 1 to minus 1, we get 0, the equivalence. And when we subtract 11 from 1, if we went around the clock, we'd end up at 2, going backwards, if that's the way we look at subtraction. Or we could realize that this is a negative number, gives us 2. But you add 2 to 2 to 11, and you get 13, which is 1 o'clock. And this one is the one I loved. A negative times a negative number is a positive number. 11 times 11 is 121. But that's around the clock 10 times with 1 left over. Whoa, this is really what impressed me. Now, where would I run into a problem? Okay, well, when we're dealing with fractions, things are a little bit different. 1/2 times 1/5 is 2 2/5. But since 12 is also 5 times 12, or 60, 1/5 of 60 comes out to 12. So 1/5 of 12 also would be 0. But turns out I find out there are 5 different choices I have. I just pick out the one that will satisfy me. So this was the first thing. When I started multiplying 12 times something, I didn't get consistently 0. I had a little bit of compromise. And then for irrational numbers, I can't find going around the clock, find something commensurate, which will fall right on the number. So the square root of 2 is 1.414, etc. I can't write it as a fraction. But what I do know is that 1.4 and 1.42 are either side of square root of 2. So I could keep getting closer and closer to multiplying the square root of 2 times 12, and say in the limit, it would come out. That makes me feel much better. But while it made me feel much better, what it doesn't do is it doesn't make me say that it works, in the same way with irrational numbers as it does with integers and negative numbers. And this is where my apology comes in, is that I hadn't thought about this and then realized that because I was so into zero being nothing, because I was taught that like the rest of you were, I got trouble. So hopefully you will accept my apology and learn math better than I did. See ya. Bye.